Thank you. Yes, that's it. Dear colleagues, as you know, my name is Karolina Kasa-Slažetić, and I am with the Faculty of Technical Sciences, University of Novi Sad, from the beginning of my studies and teaching career. Together with my colleagues, we are sending our great and warm wishes to everybody. I hope that in my presentation you will hear some new and interesting things about underground three-phase high-voltage power cable system. Please change the presentation. It is well known that the efficient electric power transmission should be achieved by the high-voltage systems, 110 kilovolts and more. Outside the urban area, the most appropriate transmission systems are the overhead systems, which due to its huge geometry and high electromagnetic field values cannot be applied in urban area. For this reason, previous urban supplying systems were constructed as a ring of power transformers stations, 110 kilovolt per x kilovolt, encircling the city, supplied by 110 kilovolt overhead transmission systems. After that, the distributional systems are applied to supply the consumer inside the city area. Increased city area with increased power consumption inside it now demands a different approach. Due to higher current inside the distribution systems, the heating losses became very high, and the conductors frequently express an overload state. For this reason, the world around is an intention to drive the high voltage system into the city area closer to the consumers. Naturally, this goal could not be achieved with overhead systems, and the cable system must be involved. Please change. Hence, in order to decrease operational joule losses, the three-phase high-voltage electrical system is frequently positioned in the middle of the consumer's area, applying buried three-phase cable system. The position of the single high-voltage cable in the constructed concrete corridors or directly buried in soil can be in triangle, in trefoil, or in line, and both systems were analyzed together with their electric and magnetic fields. The underground electric power cable system are resistant to environmental damage, to rain, snow, wind, the ice, etc., and have reduced space requirement. Moreover, due to their shielding systems, high-voltage power cables have greatly reduced electromagnetic field emission. Besides that, applying buried cable systems, the security and reliability of electrical energy transmission are significantly increased, which is very important for the consumers. The disadvantage of underground cable systems are that they heat up significantly, which leads to degradation of the insulation and their high price. Please change this. High voltage supplying cables should be buried into special corridors constructed for these cables only, or applying an already existing corridors for telecommunication system, water pipeline systems, especially in the case when high voltage cables are positioned close to any other installation. It is crucial to be familiar with the electromagnetic field produced by the cables and the influence of the field on the neighboring systems. In order to examine the high voltage cable shielding efficiency, at first we have examined the electromagnetic field of a real standardized single high voltage cable, and after that the electromagnetic field distribution of a three-phase high voltage power transmission system consisting of 3 single core high voltage cables. Those single cables do not have any ferromagnetic element, and in each of them there is one phase of three-phase power system. For the harmless application of electrical energy, the electric and magnetic field values are limited to international and domestic standards, and all the fields produced by high voltage buried cables must be less than maximal allowed values. For this reason, all calculated or measured electromagnetic field values are always compared with the values defined in standards. Please change them. The high voltage power cable in our calculations is this one in the picture. This is a triple extruded power cable applying proprietary materials on modern catenary line equipment. The foil laminate layer provides an effective water and moisture barrier and produces a limited increase in mechanical protection. Nevertheless, it should be noted that this cable must be adequately protected from potential mechanical damage too. The cables are provided with a high-density polyethylene sheet selected to offer the best compromise between abrasion, resistance, and flexibility. Due to the high-voltage cable construction, that means due to the metal electric screen embedded in the single high-voltage cable, it is expected that the electric field outside the shield can be neglected. For this reason, only magnetic field was taken into consideration in our work. Since magnetic field depends on the currents inside the cable, the magnetic flux density vector magnitudes were calculated for maximal load defined by connected power transformers. The magnetic field distribution was determined for both single cable position, flat, and trefoil position. As we can see, we have three metal layers in the construction of the applied cable. The permittivity of insulation layers are between 2.3 and 2.5, and the conductivity of this layer is 10 on minus 15 Siemens per meter. And please change the, thank you. The electromagnetic field determination is usually based on electric scalar potential and magnetic vector potential. Applying those potentials, electric field strength vector and magnetic flux density vector can be determined. We know that. The investigated electromagnetic field is in the range of extremely low frequency, and thus electric field can be calculated separately from magnetic field. Their interaction could be neglected except for electromagnetic induction phenomena. Since the explored cable has no ferromagnetic parts and the current inside the cable is harmonic, the complex domain can be adopted. The calculation of complex total current distribution across the cable's cross-section could be determined applying analytical methods, but the solution is quite complicated, and the current density vector dependence on the distance from the cable's axis is the form of Bessel functions. For this reason, the calculation described in this paper were performed numerically applying COMSOL multi-physics computer program based on finite element method. Please change the slide. The first step in the COMSOL application is the choice of the space dimension and the appropriate model. In this case, the 2D model and the AC/DC model was chosen together with electrostatics and magnetic field interfaces. The second step was the cable's geometry modeling in accordance with all layer dimensions mentioned earlier. At the same time, each cable layer was defined as subdomain with known electric and magnetic parameters. Some constant parameters for the model were defined as well. In the next step, the boundary conditions between neighboring subdomains were specified, and then the finite element mesh was generated. And we can see in the picture the mesh generated for the single high voltage cable. The last step, the solution computing could start after all these steps, and the calculation results can be presented in the form of tables graphically or as diagrams, and you will see in the next slides our results. in this picture, we wish to show the distribution of electric field, and we can see the dependence of the radial electric field strength vector magnitude on the distance from the single high voltage cable axis. As it could be expected, inside the cable conductor, including the conductor's boundary, the magnitude of electric field strength vector is 0. As you can see, here is 0. 0. Outside the conductor, the magnitude of electric field strength vector increases rapidly to its maximal value. Inside the different insulator layer, the magnitude of electric field strength vector decreases as 1 per r square to the cable metal shield. Inside all external cable layers, the magnitude of electric field strength vector is again equal to 0. So this fact means that the metal screen is really a perfect protection against extremely low field electric field. So we will take into consideration after that only the distribution, the calculation of magnetic field distribution. Please change the 3 calculated the magnetic field distribution around the 3-phase cable system in line or in triangle with the phase distribution 0, 4, 8 as it is you can see in the picture. Please change the there are different ways of burying the cable. In the picture, you can see one of them. There are other cables in the system. As you can see, in this picture, we presented the situation where the 3-phase system is directly put in the cable's embedment in the soil, but sometimes you can put the cables in concrete pipes. Please change them. Yes, and here are our results. At first, we tried to calculate the magnetic flux density vector distribution for the distribution of cables put in line and with the phase arrangement 1, 4, 0, 1, 4, 8. And in the right corner, you can see the maximal values of magnetic flux density vector RMS value. And as you can see here in Serbia, the maximal value is lower. So we have some strong, maximal value is 2.5 times lower than for ICAS, the national regulation for this type of problems. Please change the, yes. In this picture, we wish to show the distribution of magnetic flux density vector lines and for different arrangement of phase conductors. And you can see some difference in these lines, but after in the next picture, you will see that the phase arrangement does not influence the distribution of RMS value of the magnetic field. We made the calculation on 3 highs, on 3 levels, where the 0 level is on the ground surface. And as we can see, the biggest value is on the nearest distance from the ground level, and the maximum value is about 5 microtesla. Calculating the average value of magnetic flux density vector in these tree height, we calculated that it is 3.73 microtesla and is much lower below, it's much below the 40 microtesla from the domestic regulation. This graph is for the situation when the cables are 1.2 meter underground. Please change the. When the cable are put a bit higher on 0.9 meter underground, we have some increasement of the average value of magnetic flux density vector is increased, and the average value is 4.76 microtesla, and as you can see, the increasement is 27.6% comparing for the previous arrangement. With this graph, we wish to show the magnetic field, the intensity of magnetic field in the direction of y-axis perpendicular to ground level, and we have, as you can see, this red line here. The values of B were calculated in this direction, and in the right graph you can see here is the ground level, and up is the values in air, and here is in soil. And because the soil has some magnetic permeability, we have this changing in the direction of magnetic field, and we can see, for instance, in the depth of 0.4 meter, when the cable is deeper, the magnetic field value is lower than in the other case when the cable is closer to the ground level. Please change the, yes. It's this picture shows the current distribution in the middle line of all three cables. The central part is in the aluminum cable, aluminum part of the cable, and you can see that even at 50 Hertz, the proximity effect can be visible. These other values are the induced current in the other two metallic layer in the construction of the cable. Please change the. Yes, and now there are the results for the three-phase cable. Oh, I'm sorry, it's it's a mistake, no, in line, but in trefoil position with zero phase in first, as you can see in this configuration, and the maximal values. So we can compare the values with these, the calculated values with these 40 microtesla. Please change them. In this picture, we can see the distribution of magnetic flux density vector lines in the area around the cable system. I hope you can see the difference, that there are some differences when we change the phases in the cable. And please give me another slide. In this slide, we can see the values of magnetic flux density vector for 3 different heights in air above the ground, and for this arrangement, the average magnetic flux density vector is 1.02 microtesla, and it's much less than 40 microtesla from the domestic regulation. These values are for the cables where the phases 0 and 8 are 1.5 meter underground. I forgot to mention that all the calculations were made with the current of 800 amps as a nominal value for this system. When there are some different heights, it depends on the terrain where the cables are buried. When the cable is 1.92 meter underground, the values of magnetic flux density are less, and the average value is now 0.75 microtesla. And we have one more graph when the cable is on the depth 3.8 meter under the ground, and we can see that above the Earth, the average value of magnetic flux density vector is only 0.27 microtesla. And we have the similar graph for the case when for the trefoil configuration of cables. Here is the ground level, and we can compare the values in function of the height, the depth of the cables in the soil. And the current density, the distribution of current density in lower 2 cables in the center line, we can see the proximity effect and the effect, the additional effects from the detail that the cables are near one to the other, and these a little bit higher values are the induced current in these metallic layers from the conductor. At the end, I wish to mention that in 2022, the first underground 110 kilovolt 3-phase cable system is put into operation in Novi Sad. It connects 2 power transformer stations in the city. The length of the system is about 400 meters and passes through densely populated parts of the city. In order to verify the results we calculated, now we will make some measurements to verify this calculated value, and that's the next step in our project. As a conclusion, we can say that we showed that the cable metal screen is efficient, and outside the cable, the radial component of electric field strength vector does not exist at all. Hence, the high voltage cable could be positioned in already existing corridors together with any telecommunication and conductive pipeline system. Comparing the results of magnetic field calculation for maximal transmitted power with the maximum allowed values defined in standards, the calculated values shows to be also far below the allowed values. The results also emphasize that the explored cable under normal exploitation conditions is completely safe for the environment and that it can be applied in cities area with no harmful risks. And the end, I am sending greetings from Novi Sad. You can see we are on the left bank of Danube River, about 80 kilometers southwest from the capital city, Belgrade of Serbia. In the left lower corner is our faculty. Thank you for your attention.
Is any question? I think that is very lovely presentation, very good and practically oriented, which is our conference is conference about applied science, and this is really applied science. I appreciate to Carolina. And does anybody have any questions, please?
Yeah, yes, I have a question.
Yes, thank you.
My question is, if you think that in the future it is possible to transport electricity without cable, like Tesla proposed.
And yes, what will be measured then?
What?
What will be, I am asking, what will be measured then?
Oh.
Well, I will, maybe Professor Persha has some good ideas for the question of this type. Some answer, maybe.
Yes, if I can help.
Yes, thank you.
Tesla has had this idea, and he even tried to do it. Actually, this is a very interesting thing because he tried to make a standing wave between the Earth and the ionosphere. And it was not successful, of course, because it must be a very great energy consumption in this case. So he was like dominoes. He just break down all the plants, electrical plants in Colorado. He tried it in Colorado Springs. And I think that this is a brilliant idea of Tesla, but it is not real. It cannot be realistic because I don't know if you can, I think you can imagine the electric field, electromagnetic field in this case. This is entirely stratosphere in over the Earth that would be pulled off electromagnetic field. And it would be, I think it would be lethal for all living beings, including humans, of course, so I don't think it's possible to make it. The electromagnetic field for wireless transmission, I don't think it will be possible.
Thank you. Maybe in 1,000 years at the next ICAS conference, we will have a paper about transmitting the electricity in the air. Thank you.
Thank you.
You know, I also want to talk with Carolina. I saw that somebody proposed that is better that electrical car didn't use a accumulator, but maybe some trucks inside the highway. You put down on the highway. You put it some electromagnetic field, and with this electromagnetic field, fulfill, to give energy to the car to come. It means that car didn't have huge, big accumulator. Maybe somebody will be down if they have enough electrical energy from the, I don't know, from somewhere, and to on this way to put it, because electrical car have a very huge moment. One of this is if something's happened inside the electrical car and the fire will starting in the car, nobody didn't stop this fire.
Yes.
Because this is very huge accumulator, and when it's in the fire, they have a lot of dust and etc. And not water, not any. I don't know how to possibility to when you have such a situation. Also, after 10 years or 20 years, you feel this accumulator is down. And we have a lot of this accumulator which is down for 10 or 20 years, and somebody must think about it. And also this metal from accumulator inside this is deeply underground, and using this we are the good environment stay to be bad all around the world, and this is not good for the environment and for ecological view. This is some kind of electrical cars, and maybe it's good that we have electromagnetic field somewhere and go to this electromagnetic field, catching the energy and continue to drive on our car without possibility that this electromagnetic field have something on the main, doing something nasty to the driver. What do you think about it?
Thank you. Thank you. Yes, we will do it.
Yes. Persha, what do you think about it?
Well, I think that I do hope. Well, I think that electric car, completely electric car, I'm not sure if it is the future of transportation. I don't think it's a good solution. I think that hybrid cars are much better solution, because electric car, to fill electric car batteries, you need DC current. And looking for an ecological view, DC electromagnetic field is much more difficult to reduce. There's much problems with reducing time constant or DC magnetic field. And it would be the great problem into the car itself. It is a great problem during the charging of the car, of the car battery. And so I don't think that's a good solution, but it is a better solution that smoke from plants, from coal plants and thermal plants, electric plants. So this is the solution. But I do hope that the new solution will be found to reduce this huge magnetic field. It is the big problem to reduce magnetic field. You will hear from the other paper in this session that there is a very it's much easier to reduce the magnetic field, the AC magnetic field, time-varying magnetic field, because of induced currents, eddy currents, which does not exist in DC magnetic fields. So for reducing DC magnetic fields, need to be a very, very good magnetic material. I mean with high relative permeability values, and very thick magnetic material must be put as a screen to significantly reduce the DC magnetic field. So I think it's a much bigger problem that we have now with AC magnetic fields inside the cables, this time buried in the ground. This is my opinion.
Thank you, thank you. I think that we are now, Daniela. We must continue with the section.
Yes, it's time to start the parallel sessions.
Yes. It's time to start the parallel section. See you on the parallel section. Thanks to Danny for helping me, and see you on the parallel session. And thanks to all that you coming here. I saw also the Doina.
Yes, yes. Hello, Tihomir. Yes.
Wish you all the best. Tamal Sila, wish you all the best.
Thank you.
Kamal Shehari, Soan Danomi, that's super. I'm so happy.
Yeah, happy to be here.
All the friends are here, even online. Okay.
If I can say, I was a little surprised to be invited to say something, so I didn't start my speech. I didn't start properly. So now I want to say hello to everyone there.
And see you on session 1.
And
on session 1.
Yeah, sure. And I do want you a very successful meeting, a very successful conference. I do hope that I'll be part of them. I intend to attend the conference.
Next year in Hunedoara. See you together. I will take to you from Novi Sad. Wish you all the best.
Okay, hi.